In this video, we'll go over some graph basics, Dijkstra's algorithm for finding the shortest path between two nodes in a weighted graph, and implement the algorithm using PHP. If you're already familiar with graphs, you can skip ahead to the code. Pictured here is a graph. Each letter represents a node or vertex. Each line represents an edge. This is a weighted graph because we are given the distance between all of the nodes. It helps to think of a graph as a map where the nodes are cities, the edges are roads, and the weights are miles. If we have the task of finding the shortest path between A and Z, it's fairly easy to determine that we should go from A to E, then E to D, then D to Z, with a total distance of 12. Things become more complex if we have to write the code to do this, so we'll use Dijkstra's algorithm to find the shortest path between two nodes. Our first task is to represent the graph in code. We'll use a multi-dimensional array in PHP to store our graph like this. First, we'll record the distance from A to F is 1, then A to B is 2, then A to E is 6. Now we'll repeat this for all nodes on the graph. Note that we don't have to do F to A, since this is a bidirected graph, meaning that the distance from A to F is the same as the distance from F to A, which is 1. Now that we have our graph represented in code, we'll create a class in PHP. We're going to need a few private variables here. We're going to have to keep track of our nodes, and we're going to also keep track of the nodes of each neighbor in an array, and you'll see that below here in the init graph function. All we're doing is we're creating a convenience array so that we can easily iterate over all the neighbors of each node. We'll run a quick test and print out all the neighbors of A just to see if we're looking good so far. Next, we're going to initialize all of our node data. We're only concerned with 2 points of data for each node, the minimum distance to reach each node and the previous node to visit to get that minimum distance. So to initialize, we're going to set the minimum distance for all nodes to infinity, and we're going to clear the previous best node to reach it with that minimum distance. And the only other thing we have to set is the minimum distance to reach start, which is always 0. We'll print out our init data to check if it's correct. Here I'm just copying the pseudocode from Dijkstra's algorithm over to our class so we can more easily see what's going on. This next part is the heart of Dijkstra's algorithm. First, we want to iterate over all the unprocessed nodes. So we'll copy all of our nodes over to the variable q, and then we'll process each node in queue, and when we're done processing, we'll remove from queue. During each iteration, we want to find the closest unprocessed node, so we'll make a function for that. We'll run a quick test and print that out to see if that's working. Next, we want to stop our iteration when we've reached the end, or if the minimum distance to our current node is infinity. Here's where we process all the neighbor nodes of our current node. Since we know the distance from start to our current node, and we know the distance from our current node to the neighbor node, we can calculate the distance from start to all the neighbor nodes. The important thing here is if we find a lower distance to our neighbor, we update that, and we update the previous node with our current node. We'll run a quick test and print out our minimum distances in previous hop nodes to see if things are working correctly. We'll copy over the pseudocode from Dijkstra's algorithm to our update neighbors method so we can more clearly see what's going on. Next, we'll remove our current node from our array of nodes Q, and then we'll do an initial run to see the best previous node for all nodes. Since we now know the shortest distance to each node, we can walk the path backwards, starting from the end and going to the beginning, using the shortest path possible. I've added in some extra output to help illustrate finding shorter paths to nodes. The majority of our neighbor processing is going to be updating from infinity to a known number, so we'll ignore those and we'll only output when we find a shorter path to a node. You can see we previously found a path to D via C at a distance of 9, but we found a better path to D via E with a distance of 7, so we'll use that path. I hope this video will help you out implementing Dijkstra's algorithm in PHP. If you've made it this far, please give me a thumbs up and consider subscribing. You'll find a link to all this code in the description. Thanks for watching.